Just a minute, I think I have something else. Just a few minutes. Okay, I lost connection. Can you see my slides now?
Yes, ma'am.
Okay, so let's not waste any more time. So I'm going to initially go over ground we have already covered in the previous class, because I realize that some of these techniques which we have discussed, they are not very simple, and I must tell you students again and again that the only way you can really come to grips with these techniques of a finite state machine conversion from say epsilon NFA to NFA and then NFA to DFA, the only way is to practice a lot, take many examples and practice. Now I'm going to share a list of assignment questions, some of them worked out, and all of you have to very religiously solve all those problems. Okay, this is just like a mathematical subject, okay, where unless you solve a lot of problems, you will not get a feel for all these various techniques. Okay, so today I will actually cover old ground. So let's first start with the conversion of an epsilon NFA to NFA. Okay, so that is the equivalence of an NFA and epsilon NFA, to show that they accept the same kind of languages, the same language which is accepted by an NFA is also accepted by an epsilon NFA and vice versa. Okay, so NFA to epsilon NFA, actually that is trivial. Please mute yourselves. Can you hear me now? Students, can you hear me?
Yes, ma'am.
Okay.
Yes, ma'am.
If you lose audio, if you cannot hear me, please try to inform me immediately. Okay, because I find that the audio is switched off without any, I do not know how it is switched off automatically. So let's look at this conversion of an epsilon NFA to NFA. So what we are going to do is basically combine states and create subsets, as we have seen in the last class. Okay. So to construct an ordinary NFA, we have the same set of states as epsilon NFA. The input alphabet also remains the same. Okay, start state also remains the same. But final states and of course the transition function is what are going to make differences. Now final states we have seen that we are going to replace these states, each transition to a subset by transition to a single state. Okay, so transition function will change and the set of states such that the epsilon closure, all those states from which through epsilon transitions only you can reach a final state in the original NFA, all those states will now become final states themselves. Okay. This again, people are disturbing. Please mute yourselves. Please check that you are muted. Okay, so this diagram, I hope all of you remember this. So these triangles, they represent epsilon NFAs and these are transitions on A. So suppose you are a state here. From here, when you are replacing the transition, the epsilon transitions by a single transition, you will put a transition to the set of states here. Okay, so we go from here to here. So, okay. And the intuition is that you take all the epsilon transitions before A, but not after A. Okay, so as you remember, we discussed, we will treat A as epsilon star A. That means many epsilons before A, 0 or up to infinite, any number of epsilons before A. Okay, so that was, if you remember, we called it epsilon star A. So epsilon star, this convention is actually the convention of what are called regular expressions, which we will be discussing in the next class. In fact, Shubhrajit sir will be discussing in the next class. And so this means that there can be 0 or more incidences of epsilon. So you can think of all these as epsilon paths and ending in A. But usually we do not take the epsilons after A. Now, this example also we had discussed. So this is where you can see here all the others are simple actually, they remain the same. But here from E on 1, on input 1, you are adding transitions to both C and D. And why are you doing that? Because the epsilon closures of E contain B and C. So B and C is appearing here, as you can see. And therefore, and from B and C on 1, you have transitions to C and D. So from E itself, because by epsilon transitions, you can go to B and C. Okay, from E with epsilon transitions, you can go to B and C. Therefore, from B and C also, you can take the outgoing 1 transition. Therefore, the destinations of those transitions, that is C and D, also appear here. Okay, so effectively, if you put it mathematically, the transition function of the non-epsilon NFA, of the NFA, that is delta n, is obtained by replacing delta epsilon. Delta epsilon is the epsilon NFA, the transition function of epsilon NFA. Okay, by replacing delta epsilon QA by delta epsilon of epsilon closure QA. So what is the epsilon closure? To go back to the previous slide, the epsilon closure of E is B, C, D, E. Okay, so epsilon closure of this, where it is going on the input, here A is 1. So input 1. So all those states are appearing as the destination. Okay, so the mathematical expression would be the transition function delta n is obtained by replacing delta QA, so you can see that here, by delta epsilon closure QA. Okay, so this is what we have seen as per the previous diagram, the previous example. But there is another option, another possibility. In fact, the second possibility is the one which you will find in your textbooks. The textbook, I think we have already, have we discussed, have I told you what is the textbook? Yes or no?
Yes, ma'am.
Okay. In case people do not know, I'm just writing down the names. I think I went wrong with the name. I did not tell you the names.
Ma'am, you told Ullman and then Martin, both the
Yes,
textbooks.
Motwani Ullman. So this is the main textbook. Okay. An older version of this textbook has only Hopcroft and Ullman. Okay. That is an older version. The newer versions have Motwani also as an author. The newer version is slightly easier to read. The older version is mathematical. In fact, both sir and I, we prefer the older version because that is the one we studied when we were students. Okay. So, but the newer version is also equally good and you can follow either of them. We will be basically in this course following the conventions given by this, these authors, okay, Hopcroft Ullman and Hopcroft Motwani Ullman. In addition, I also follow the book by Martin. Okay, and sir, I think also will be referring to another book, if I'm not wrong, it is Sipster.
Yeah, it's Michael Sipser.
Yes, Sipser, not T, I think. T is not there. Anyway,
yeah,
please check up. I think you know it better. Okay, so these books also you can follow. Some things we will take from here also. Okay, and altogether, and we will give you enough assignments. And as I have already told you before, please pick up any book you get and try to solve the problems for there. For problems, all books are good. Okay, and please do not be confused by slight minor changes in convention and etc. But as far as this course is concerned, we will follow the conventions in this book, which is your textbook. Okay. Now, if you look at your textbook, you will find that this transition function here for epsilon NFA to NFA, it is not defined like this. Rather, it is defined as this, where you replace delta QA by epsilon closure delta QA. In fact, to tell you the truth, I have always followed the second option and it is only now that I am encountering the first option. But both are correct. In fact, these slides, most of these slides, they have been provided. I have also put the link at the beginning of my presentation. They are the slides which are used by Jeffrey Ullman himself in Stanford University. Okay, so in the slides, he presents this particular option, which we have used in the previous example. But both options are correct. Okay, so today let's also discuss the second option of creating the transition function of the NFA from epsilon NFA. Okay, that is, instead of replacing by a delta epsilon closure QA, you will replace by epsilon closure delta QA. Okay, so what difference does it make? To show the difference, first let me go back to a previous diagram, this one. Here, actually, epsilon closure delta QA will take you not from here to here as shown, but rather from here to here, as I had initially shown you in the previous class. Do you remember? Okay, so just to be a little more clear, let's take an example. Okay, so let's work out this example. So I have already drawn part of the example in the slides. Now we will look at this epsilon NFA given here. Okay, can anybody describe the language accepted by this epsilon NFA? What kind of strings do you think will be accepted by this epsilon NFA? Why I'm not getting any response? We have been discussing enough finite state machines already. So you should be able to tell me. How will you describe the set of strings which is accepted by this epsilon NFA shown here?
The strings that has alphabet C.
Only C? What about, say, the string A, B, C? Will it be accepted?
Yes, ma'am.
Yes. Okay. So you follow these A transitions, A,
And it has
then
at least
epsilon
one.
transition to B. Okay. Then epsilon transition C. What about, say, A, B, B? What about this string? Will this be accepted?
Yes,
Yes, ma'am.
yes, ma'am.
Yes. Okay. So now I think, okay, what about B, C, C? Yes or no?
Yes, ma'am.
Yes. Okay. What about A, C, B, B?
Yeah, yes, ma'am.
Yes,
No,
ma'am.
it won't work, ma'am. No, ma'am, it will work. It will work, ma'am. It will
Yes or
work.
no?
Yes,
Clearly.
Yes, ma'am, it will work, ma'am.
yes, ma'am.
How?
Ma'am, A will self loop back to A. Then
There's no
is
looping back unless there's a transition. Okay. A self-looping. Then
acha, C will cut it off. That C has no transitions forward. But there is epsilon.
epsilon, but it is shown in one direction, right?
Okay, acha.
You cannot take an arrow in the opposite direction. You have to follow it in the correct given direction. So this will not be accepted. But if I remove this B, this will now be accepted. Okay. So the set of strings accepted by this NFA is all those strings where you have 0 or more number of A's followed by 0 or more number of B's followed by 0 or more number of C's. Okay. Can you see that? So 0 or more number of A's followed by 0 or more number of B's followed by 0 or more number of C's. Okay, so that is the set of string. That is the English-like description of the set of strings which will be accepted by this NFA. Okay, so let me rub this out. So now if you look at this NFA again, so epsilon closures of these three states A, B and C, we have the epsilon closures of we can find the epsilon closures. So what is epsilon closure? All those states to which you can go without consuming any input. That means following epsilon transitions only if necessary. So epsilon closure A contains A, B and C because of this epsilon path. Epsilon closure B contains B itself. Always the same state is always there because you can always continue to stay in the same state without accepting any input, right? So B and C, and epsilon closure C contains only C. So this is just for our convenience. Is this clear up to this point? And this NFA, this epsilon NFA, we can represent by this transition diagram. So the states A, B and C, the inputs again A, B and C, that's a little confusing, but a small a, small b and small c and epsilon, and these are the transitions 1, 2, 3, 4, 5. So 5 transitions 1, 2, 3, 4, 5, 5 transitions. Can you see that till this point? All of you very clear? Any doubt here? No response. Any of you have any doubt? If not, I'll assume there's no doubt. Okay. So now we are going to look at the first option of creating a transition function. So let's go back.
The last 28 days, there were 102 new page likes, 4307 post tweets,
I think that was noise. Anyway, so the first option is where you replace epsilon QA by epsilon, delta QA by delta epsilon closure QA. Okay. So if you do that, this is the transition table you will be getting. So delta QA, delta from state A on A, you will go to A itself. Okay. So this, for this, to find this, you will find delta epsilon closure A. Okay. So what is epsilon closure A? A, B and C. And you can see of A, B and C, only A has a transition on small a. Okay. On input A. So here we just put A. What about B? Input character B. From A on input character B, you do not have a transition directly, but epsilon closure A contains the sets, contains the states B and C also. And both B and, B here you can see has, B here you can see has a transition on B. Okay. So you go to B also. So you find that B has been added here. Can you see that? We are doing this the way we have done the previous example. Okay. So what are we doing? Epsilon delta QA we are replacing by delta of epsilon closure QA. So we are finding the epsilon closure first. So epsilon closure is of Q is this triangle, and from here A, the transition on A. So we are finding basically this set here. Okay, so we go from here to here. So by following this, we find this particular transition table. Okay, and if you want to draw the diagram will be something like this. I'm just drawing it quickly. Okay, and now since all of these epsilon closures, they have the final state C. So all of these states are now final states.
Final state.
Okay, so that is clear. Initial state remains the same. Set of states remains the same. So A, B, C. Okay, now let's put in these transitions. From A on A, you have this self loop. From A on input B, you will go to B. Okay, and from on input C, you will go directly to C. From B on input A, you do not go anywhere, because if you have seen a B already, then you cannot see an A anymore. Okay, remember, 0 or more number of A followed by 0 or more number of B followed by 0 or more number of C. Okay, so from B, you have a self loop on input B, and on C, you will see C. Okay, and from C, you only have a self loop on C. So this is the NFA which we get by following this first option. Can you all see this NFA? And are you all convinced that this NFA will also accept only the strings which this previous epsilon NFA was accepting? Okay, so if you have 0 or more number of A's, you loop here as many times as you like. Then if you see a B, you cannot go back to A again. You have to see 0 or more number of C's, and you can stop there if you wish. Or if you see a C, you go to the third state and you see 0 or more number of any more number of C's as you like. Okay, and from the, and remember, strings like just C, CC, those are also part of the language, because you are allowed to see 0 number of A's and B's. Okay, so you can directly go to C also. You can directly go to B also from the start state. So this NFA, we can see it accepts the same language as this previous NFA. Now we are going to see the second option of creating the transition table, which you will actually find in your textbook. Okay, by this option, what does it say? Let's go back to the previous slide. So the second option is to replace delta QA by epsilon closure of delta QA. Okay, so that's not too difficult. So delta QA here, delta QA, this is A. So instead of A, we will write epsilon closure of A. So that is A, B, and C, as you can see. Okay, so delta QB, this B is not here directly, but you have to write epsilon closure of this. Okay, so actually by following epsilon transitions, you can go to B. Okay, you can go to state B where you can accept B. So therefore, you have to give the epsilon closure of B, which is BC. And similarly for C. Okay, so instead of just one set, you go to a subset of states. So these are nothing but the same states, as you can see, replaced by their epsilon closures. Now, if this option of the transition function is followed, then what is the NFA which we get? Let's draw it again. Mute. All of these are final states. So this is A, B, C, and this is the start state. Okay. And let's now put in the transitions. So from A, you have transitions to A, B, C, all of them. Okay. So you have one transition to A, one transition to, I'm sorry, where am I? Okay. One transition to A, one transition to B on A, and also one transition to C. Then from A on B, you go to B. So this is another transition on B, and you also go to C. Mute. Please mute yourself. Don't disturb the class. And from A on C, okay, this we have finished. Okay, and from A on C, you go directly to C. Actually, this is another transition. This was A. Okay, so A, B, and C, all of them have transitions to C. From B, you go to B directly. So this B transition, and you go to C on B. Okay, and if you see C also, you go to C. From C, if you see C, you have a transition on C. This is actually small c. Let's not make a distinction. Let's make it very clear. This is C. Right? So this is the NFA which you get using the second option of finding the transition table. Now let's check and see whether the same strings are being accepted. What do you think? Please tell me. I'll leave it to you. I'll give you a minute or two. Tell me whether it is accepting the same strings as the other two NFAs, or is it accepting a different class of strings? Can you find any string which the previous NFA was not accepting, which this NFA is accepting?
No, ma'am, I don't think so.
Or can you find a string which the previous NFA was accepting and this NFA is not accepting? No, it is not, because these are actually equivalent. Okay, so both of these options, they give us correct transition diagrams, they give us correct NFAs, okay, which accept the same strings as this previous NFA. Only you can see in the second option there are many more arcs, okay, and it is a slightly bigger, a slightly more complicated NFA. That is the only difference. But please remember, so what is important here is not just that the both options are possible. Okay, you might find the second option in your textbook and the first option in your slides. Both are correct. If you wish, try to follow the first option because it's giving you a simpler NFA. Okay. Now, what is important to note here? Yes.
Ma'am, I don't remember seeing these slides. Ma'am, will you update these slides in the
I have
PDF?
mailed you the slides. I think I've mailed you after
Ma'am,
the
it's not
previous.
in the original slide. Ma'am. This example is actually not
This
there.
example is not there. This example I'm doing today.
Okay.
This example, please try and copy it down. You still have some time before I move away from the slide, and you work it out yourself. Work it out yourself. Okay. So, important point to note here is that for the same language, it is possible to have more than one NFA, more than one epsilon NFA. So number of different NFAs, in fact, number of different DFAs might recognize the same language. So please realize that suppose I give you a particular English-like language and I ask you to create a finite automata for it, okay, either NFA or DFA. It is possible that each of you will give me a different finite automata and all of you could be correct. Okay, so a finite automata is not necessarily unique, but there is a version of finite automata which is unique, which we'll see today. Okay, and this version, this is called a canonical form or a normal form. This is nothing but the minimized DFA. But before we go to minimization of DFA, I'm going to solve a few more examples. I hope you have copied this down. Just copy down the epsilon NFA, rest you can work out. And I'm going to go to the previous slide. Please copy down the two options of transition functions. Can I move from here?
Yes, ma'am. Could you just go to that slide, ma'am?
Just copy down this epsilon NFA. Rest of the example you can work out yourself. You're supposed to be able to work out yourself, in fact. Okay, so I'm going to the previous slide. Please copy down these two options of transition functions. Okay, what I have underlined here and what I have underlined here. Are you done?
Ma'am, 1 second, ma'am.
Okay. I think I can move.
Yes, ma'am.
Okay.
Done.
Okay, fine.
Yes,
So this example, please work out yourself. Okay, find these two NFAs which we have done, we have got on the screen by working out using both the options of transition function. If you do that in future, actually, I think by now you should realize that the second option is just taking you from here to here. It is allowing epsilon NFAs afterwards also. Okay, so these are the two options. Now let's go for conversion of NFA to DFA. This also we have discussed in the previous class, and we have discussed an example also. This theorem we have seen how a single state of a DFA actually represents a subset of states from the NFA. Okay. So the subset construction algorithm actually is more or less like a proof. So just to cover old ground, the states of the DFA are actually subsets of NFA. So the set of states is the power set, okay, 2 to the power q. Input alphabet remains the same. Start state remains the same, only now you call it a subset of one state. Final states, all those which have members of the previous set of final states. Okay, so something like delta NFA to NFA. Okay, if you have a previous final state, then this present state also will be a final state. And now for the transition functions. Okay, so this example again, I must go to slideshow mode. I'll just show you there. Okay, so this example again we have seen in the previous class. I'm just showing it to you. Now you have the NFA on the left. Okay, I want all of you to work through this example and solve to get the DFA, which we will now see. Okay, so the first step is to enumerate all possible subsets. This is just following the conversion algorithm theoretically. So this is the power set. Please mute yourself. Please don't create noise in class. Check that you are muted. So all the sets, which can be all the possible subsets. So this is the power set of the set of states of NFA. The initial states, as you know, is going to be Q0. The final states we'll see later. Now, so let's determine the transitions. So how do we find the transitions? Transitions we have seen for every component of a subset. Okay, we have to find all those sets in the NFA to which there will be a transition on a particular input character. Okay, so let's take input character, say 0, and let's take this subset Q0, Q1. Okay, so from Q0 on 0, you have transition to Q0 itself and also Q1. Okay, so put Q0, Q1 in the destination. And from Q1, where is Q1? Q1, you do not have a transition on 0. So no other state is added. So the subset will be Q0, Q1. Okay, let's take Q0, Q2. And okay, let's for Q0, Q1, let's take the input character 1. So from Q0, Q1, Q0 on 1, you go to Q0, as you can see. And from Q1 on 1, you go to Q2. So we put Q0 and Q2 both in the destination. And this is the subset now. So these subsets are created in this manner. You have to treat each of the states in the source subset individually. Okay, so by this, now the set of transitions have been created. Okay, this is the form of a table now. Now, next step is to retain only those states which are reachable from Q0. A number of states have been created, all of, because we have basically looked at the power set. Okay, all of these subsets may not be required because we really cannot reach those subsets by any path which starts at Q0. And remember, Q0 is the initial state. So you will only follow those paths which start from Q0. Okay, so if we now start from Q0 and start following all the paths, you find a number of states are never going to be used. Okay, so delete those states. So these are the states which get deleted completely. Okay, so we retain only those states which are reachable from the initial state. So the transition function table, you find it becomes smaller, much smaller. Okay, and if you draw the diagram, this is like this. Okay, so this is the fundamental NFA to DFA conversion by subset construction. Okay, by subset construction, constructing the power set and then finding transitions. Okay, and so on. But as you can see, we have done a lot of work which we had to throw away actually, because there are a number of sets which we are not going to be subsets, which we are not going to be using. So it's no point in working out the transitions from these subsets. So what we do next is we follow a lazy creation of states. These states are being created, or these subsets are being created in a lazy manner as and when required. So this is the lazy creation, same example to work out again. Start with the initial state. Initial state is going to remain the same. It will have to be there in every path. Okay. Find those subsets which you reach from the initial state. So you have added, you can see one of them is the same state. The other is a new state which you have added, Q0, Q1. So try and find the transitions from Q0, Q1 now. And you find there's another new set which we have not yet explored. Okay. So that is Q0, Q2. So find Q0, Q2 and the transitions from Q0, Q2 on every input in the input alphabet. Okay, and you find that no more new subsets are being added. That means all other subsets are actually useless states which are not going to be used. Okay, and out of the 3 subsets which we have added, one of them is the final one, because the final state in the NFA was Q2, and you can see only Q0, Q2 has that final state. So that is going to be the final state. So introduce states as you go on a need basis. And when you draw the diagram, it is the same DFA as before. So this is a slightly more clever way of going about it. And to put this in an algorithm form so that you can code it easily. Okay, this algorithm also, I think this I have included in the slides which I mailed to you. Have I included them?
Yes, ma'am.
Okay, so this algorithm was there. So I hope you can work through this algorithm. So let's escape this now. Okay, so this is the algorithm. Okay, and this algorithm actually is a very, very useful algorithm. There are certain points to this which you will realize as we go on. One important characteristic is that this algorithm you can apply directly to an epsilon NFA also. Okay, you don't necessarily have to convert the epsilon NFA to NFA and then apply the algorithm. So this algorithm you can apply directly to epsilon NFA. And this mark unmark is nothing but keeping track of which states we have explored and which we have not explored. So don't be confused by that. Have you all been able to understand this algorithm? If you take the previous example, this one, NFA, and apply this algorithm, you will find this DFA which is shown here. Okay, so you have the initial NFA and the DFA work out by applying this algorithm. But today we'll take another example. Okay, so work out this example now using the same algorithm as before. Okay, so I have drawn another NFA on the screen. Please draw this NFA in your class note copies. All of you, I hope all of you are keep maintaining a class note copy just to keep track of where we are going. So take down this NFA and let's work out by using the previous subset construction, lazy subset construction algorithm, which has been shown. Okay, so first tell me what kind of strings are accepted by this NFA. All of you convinced that this is an NFA?
Yes, ma'am.
Why is it an NFA?
Ma'am, because like 0 is going both to Q1 as well as Q0 back.
Yes,
so
yes. Because of this one outgoing transition to two different states, this is not a DFA, it is still an NFA. And you have only one accepting state, as you can see, that is Q2. So what kind of strings are accepted by this NFA? How will you express that in normal speaking English?
Ma'am, strings containing only of zeros and ones.
Binary strings.
Binary strings.
Ma'am, a string ending in 0 and 1.
Which is ending in 0, 1.
Ending
in 0, 1. Okay. So strings consisting of zeros and ones which end in the substring 0, 1. Okay. So they have to end in the substring 0, 1. That is all. So this is the language which is accepted by this NFA, and we are going to have to create a DFA for it. So first of all, let's create the subsets by this lazy subset creation. So we start with the initial state, which is Q0. Now we are putting it in a subset. We start with a subset consisting of only the initial state Q0. Now from Q0 on input 0, which are the states we go to? You can see that we go to Q0 itself and Q1 also. Okay, so that is why it is an NFA after all. Okay, and where do you go from Q0 on input 1? Where do you go?
Q0 only.
Q0. Okay. And no other state. So this is all right. So we have added two subsets. Okay. So we have basically added two transitions. Okay. To our finite automata. And these two subsets, out of this, we find that Q0 is already there in this list. Okay. This list. So this is actually a marked state. But a new state or new subset has been added, that is Q0, Q1, which we have not explored. So let's add this here. Okay, and let's explore this Q0, Q1. So from Q0 on 0, where do we go? So let's start creating the subset. We go to Q0 and Q1 as before. And from Q1 on 0, where do we go? There's no outgoing transition. Okay, so this ends here. Now, for input 1, from Q0 on 1, which state do you go to?
Ma'am, Q0 and Q2, ma'am. That's a subset.
Q0. Okay. And from state Q1 here, where do you go to on input 1? You go to Q2. So this is a new state which you have added. You can see Q0, Q1 already has been explored. Q0, Q2 is a new state which we have added. So let's add Q0, Q2.
Ma'am, it gives Q1, Q2 in 0.
Q0, Q2 on 0, it goes to Q0, Q1 as before. Okay, and here it goes to Q0 because from Q2 actually there are no outgoing transitions. So this row is actually a replication of the first row of only Q0. Okay, so this is now the transition function, and what we can do to simplify this is actually put names to these subsets, put logical names. So suppose this we call A, this we call B, this we call C. So we can draw the transition table again.
Ma'am, I have a doubt, ma'am.
Yes.
Ma'am, why wouldn't Q0, Q2 go to Q1, Q2? Because Q0 also goes to Q1 due to 0.
Q0
goes to Q1 also due to 0. We could also write it that way, right?
Right, we have written Q1.
No, ma'am. Q0 goes to Q1, not Q2. Q0 goes to Q1 for 0.
No. Wait. Which state are we talking about? Which row? First, second, third?
Ma'am, the third row, ma'am, where Q0, Q2
Q0,
is
Q2. Yes.
Upon 0, Q0 goes to Q1 and Q2 does not change. So it would be Q0, Q2. Say it would be Q1, Q2. Q1, Q2 or upon 0.
Look at the components of the subset individually. Now remember the components of the subset are in the NFA. Okay, so Q0 in this NFA on 0, where do you go? You go to Q0, you go to Q1. Okay, from Q2 in this NFA, where do you go on input 0? You don't go anywhere. Exactly. There's no outgoing. You don't even stay in the same state. That this outgoing transition is not defined. Okay, so it is not going to give you, if you had to stay in the same state, you would have had it to add a transition like this, which is not there. Please remember, right? So no new state is being added. Is that clear? Does that clear your doubt?
No, I'm not really on that. How is it going to Q1? Like how are we getting Q0, Q1 in that case? Are we just repeating the state on the earlier row?
From Q0, where do you go on input 0?
Either Q1 or Q0.
Q1 or Q0, both are there.
Okay. That's just for okay, ma'am. Now it's clear, ma'am.
Right?
Yes, ma'am.
Anybody else have any doubt how the subset is created?
No, ma'am.
Okay, so let's go to the next step. That is, what we are doing is These subsets now, instead of calling them Q0, Q1, Q0, Q2, etc., we are just going to give them names. So let's give them names like A, B, and C. Input alphabet remains the same. So the transition function is now, so this is B, this is A, okay, B, C, and this is B, and this is A, right? And the finite state machine, if you want to draw the a graphical representation, okay, so this is your initial state, and because of these subsets, Q2 appears only in the last one, so this is now going to be the final state. Okay, so Q2 is going to be the final state, or which we call C now. So C is going to be the final state. Okay, so this is the start state, A, B, C. Okay, from A on 0 you go to B, A on 1 you stay in A, from B on 0 you go to B, so you have a self loop here. B on 1 you go to C, from C on 0 you go to B, and from C on 1 you go back to A, because you have to start all over again to find the last 0, 1. Okay, so this is on 1. So this is now going to be the DFA, which represents the same language, which accepts the same language. That means strings of zeros and ones, they can be as long as you want, but they have to end in 0, 1. Okay. Is this clear? Is the subset construction now clear to all of you through this example?
Yes, ma'am.
Okay. So I think we should now proceed. So we have just FSM minimization left, and then we can stop for today. And FSM minimization, I do not expect you to have any problems in understanding, because we have basically covered the fundamental principles in digital logic design course itself. So DFA minimization. Now, why is it important to do DFA minimization? Please remember, the minimized DFA is actually a normal form or a canonical form. Now, I have already told you what is a normal form. Now, suppose I give all of you a particular language and I ask you to create a finite automata. Okay, all of you are going to give me different finite automatas. Even if all of you stick to DFAs only, you can maybe produce a number of DFAs which accept the same language. Okay, so there is not going to be a single one. But if I insist that all of you, all the DFAs must be state minimized, must have the minimum number of states, that means they should be in their minimized form, then you will find that everybody produces the same DFA. Okay, so if there exists a particular representation which is going to stay the same, however we construct it, we can all follow different construction procedures, but if we end up in the same output, then this particular form of output is called a normal form or canonical form. Okay, that there is a big advantage to having a canonical form. That means if we can produce a finite automata, suppose we have been given two different languages expressed maybe in English, but using different language, different phraseology. Okay, and we want to find out if they express the same language or not, whether they accept the same strings or not. So what we can do is we can create canonical DFAs for these two languages, and if the canonical DFAs end up in the same DFA, and if they end up to be same, then we know that these two languages are actually the same. So we can compare DFAs only when we have a canonical form. Otherwise, whether it is NFA or whether it is DFA, the same language can produce a number of different DFAs and NFAs. Okay, so that is the importance of a canonical form, and the minimized DFA will always be the same if it is if it is the same language which is being expressed. Okay. So the DFA minimization is the task of transforming a given DFA into an equivalent DFA which has minimum number of states. So in some texts you will find this is called the state minimized DFA. Okay, because remember DFA is not only states, there are also transitions. You might say, why not reduce the number of transitions? Maybe an extra state or so, doesn't matter. No, the state minimized DFA is going to be called the minimized DFA. Okay. So the DFA which you produce by subset construction procedure are already in their minimized form. So if you have been following the subset construction procedure which we have done before, particularly the lazy construction method, then you automatically produce the minimized DFA which is canonical. Okay. So this subset construction algorithm is a very, very powerful algorithm. Not only does it allow you to create a DFA from epsilon NFAs also if necessary, but it also produces a DFA which is already minimized. Okay, so that's an added benefit. But it is possible that you have been given a DFA which is not state minimized and you're asked to minimize it. Then how will you go about it? Okay, so let's first look at distinct states. Okay, so two states P and Q are distinct. Say if one is a final state and the other is not a final state, then they can never be the same and they can never be equivalent. They are always distinct. Okay. And if there is some input character A for which, okay, some input character in the input alphabet for which delta PA and delta QA are distinct. Okay. So for example, there are two states P and Q. Okay, for some input character you find that for all of the input characters this P and Q are actually transitioning to the same destination state. Okay, but if you end up in finding some input character A for which say P goes to some state and Q goes to some other state, if you can find an input character like this, then you can say that P and Q are not the same state, not equivalent states, and we cannot treat them as a same state. Okay, so the minimized DFA is obtained by merging those states which are not distinct. Okay, so first we have described what are distinct states. First of all, a final state and a non-final state, they are not distinct. They are distinct. They are not the same. Okay. And also if there exists some input character for which one goes to one state and the other goes to a different state, then they are not the same and you cannot merge them. So if you think back in digital logic, when we were doing state minimization in finite state machines, how did we do it? Does anybody remember? Can you tell me?
Ma'am, we will be drawing a state table of the automata.
Yes. Yes. And then what did we do?
Then we will be finding the states which will produce same output on the same input. Then we will be replacing the one state with another.
All instances of the state.
We will be merging those two. So what we were doing is, see, please remember, there we did it mechanically. Okay. Now you know exactly what we are doing. There we were looking at the state transition table. Okay. The transition table and trying to find rows which were the same. Do you remember? If the rows were exactly the same, we were merging those two into a single state. Okay. So these rows are nothing but transitions. And if the transitions are going to the same states, then those two states were treated as equivalent and merged into a single state. Okay. So merging two states, you might find that another two rows have now become similar. Okay. So then we were merging that, and this we were doing iteratively. Do you remember that? Okay. And if you find a minimized DFA, your circuit is going to be smaller. The circuit which you design from that DFA is going to be smaller, and so on. Okay. So that is exactly the process of finding distinct states. Okay. And keeping them and merging those states which are not distinct. This is what we have been doing. Now let's do it in a little more, rigorously, let's say. So the DFA minimization algorithm, how it proceeds. This is basically a partitioning algorithm. I hope all of you know what is a partition of a set. Can you define a partition, or at least explain what it means? How do you define partitions in a set?
Ma'am, like two segments that do not have any intersections between each other, like two mutually exclusive segments of a set.
Not necessarily two, it could be more than two also. And what is important is that all elements of the set must be covered.
Yes,
They
yes.
must fall in some partition or the other. Okay, so like if the set is one big room, and you have to make partitions such that all the space in the room is covered and every element falls in one partition or the other. That is the partitioning of a set. I'm sure you have done it in discrete maths, in set theory. Okay, so here we are following an algorithm which uses this partitioning technique. Okay, so we will be actually doing this partitioning, and also we will be going iteratively as we have done before. Okay, now once we do this, you will realize that what we were doing in digital logic was exactly the same. We were following exactly this iterative method. Okay, so we start with two partitions. One is the set of final states and the other is the set of non-final states, because we have already seen that final states and non-final states are never equivalent. Okay, so two partitions, and all these partitions, they represent different states, distinct states. Okay, so the first partition is denoted by P0. P0 is the partitioning of final states and non-final states. So two different blocks, you can say, now exist in the set. For each partition, okay, in PK, suppose K is the kth iteration we are in, two states X and Y are divided into two partitions if there is an input A such that delta XA and delta YA have destinations in different partitions. What this means, what does this mean? What it means is, suppose you now have a set, okay, you have a set and there is one partition here in which there are two states X and Y. Okay, there could be more, but two states at least. And you find there is some input character for which from X you go to a state which is in one partition. Which state, it's not important as long as we know which partition. And for Y, if it goes to the same partition, that is fine. That means basically these partitions represent a single state. Okay, and if it goes to the same partition, then we still know that X and Y are actually, they could be the same state, non-distinct. Okay, but if X and Y go to different partitions for some input character, then X and Y cannot continue to stay in the same partition, and you have to break this partition into two separate partitions. Do you understand what I am saying? So let's read this statement again. For each partition in PK, okay, PK is a partitioning of the states, so different. So if two states X and Y are divided into two separate partitions, as here, if there is an input A, this is the input, for such that delta XA and delta YA are in different partitions of PK. Okay, if they go to different partitions, you know that X and Y cannot be kept in the same partition. Is this clear? And this you go on doing iteratively. Once you break partitions, you make smaller blocks in the partition, and then you check again, do the entire checking all over again and see which states have to be, which partitions have to be further broken. If PK and if you find for two consecutive iterations that you are not changing the partitions remain same, they are not further disintegrating, then it means that you have found the final partition. Okay, so final partitioning and combine the equivalent states in each partition. So now when further breaking up is not happening, you might find that this particular partition has three states, this has 2 states, this has 1 state each. Okay, and each of these partitions or blocks, okay, for this partitioning, when it has stabilized and is not further disintegrating, this will represent 1 state in the final DFA. Okay, so combine the equivalent sets in each partition and make them the new sets of the reduced DFA. So this algorithm, what it does is it starts with as many states combined as possible and disintegrates the partitions. And what we were doing in digital logic was just the opposite, but the same thing. What we were doing is we were trying to find 2 states which we could combine to reduce the number of total states or total partitions in the final state machine. So we were doing a combining procedure. Here we are doing a disintegrating procedure, starting with the smallest partition of just 2 states, final and non-final. Okay, so this is the only distinction. Otherwise, it is exactly the same. I hope all of you have understood the concept of distinct states. If you understand that, then this is not difficult. And finally, let's take an example. This is going to be the last slide, so I'm not going to keep you much longer. So this final state machine on the left, is it an NFA or is it a DFA? And what language does it accept?
It's a DFA.
It's a DFA. And is it possible to understand what language it accepts? I think it's pretty complicated. It's not so easy to understand. If it had been an NFA, it might have been easier to read. Okay, so yes, last class I believe people were asking why we need NFAs. Actually, we do not need NFAs, but sometimes NFA is easier to read, and when we are converting from English-like language to a finite automata, NFA might be more intuitive, easier to form. And if we can form a correct NFA, we can always make a DFA out of it, because now you have studied all the algorithms. Okay, so this is a DFA and we are going to try and minimize it. Okay, so here you see the transition function of the DFA is also given. Q0 is the initial state and Q4 is the only final state. There are 5 states. Okay, now if we try to follow the approach which we did in the previous semester, it appears that Q1 and Q3 can be combined together, right? See, Q1 and Q3, they have the same rows. Okay, so if we combine Q1 and Q3, then any other 2 rows can be combined. Actually, we have to do it iteratively. So let's follow the partitioning procedure. So how do we use this partitioning algorithm? So we start with the initial partitioning, that is final states and non-final states. You can see here P0, this is our initial partitioning. So we have, so this is the initial part. So we have 2 partitions. The first is the partition of non-final states, Q0, Q1, Q2, Q3, and the second is the partition of final states, that is only Q4. Okay, now look at the outgoing transitions on input characters. From Q0, on 0, we go to Q1, which is the same partition, and Q1 and Q3 on 1. Okay, from Q1, which is this state, we go to Q2, which is again the same partition, and Q4. So obviously Q0 and Q1, they cannot stay in the same partition. Can you see that? Why can it not stay in the same partition? Because there is one input character 1, okay, for which Q0 goes to the non-final partition and Q1 goes to the final partition. Can you understand that? Why Q0 and Q1 are distinct states?
Yes, ma'am.
Okay, because we have already found an input character 1 on which Q0 goes to the non-final partition of P0 and Q1 goes to the final partition. Now let's look at the other states here. Q2, again, Q2 is similar to Q1. Okay, the first one goes to the same partition, the second transition is to the final partition, and Q3 also is similar to Q1. So these three states, they stay in one partition, but Q0 has to be separated out. It is going to a different set of, it has a different set of transitions. Okay. So in the next iteration, that is P1, in the partitioning of P1, we find Q0 has been separated out, and Q1, Q2 and Q3, they continue to be in the same partition, and Q4 of course has always been in a separate partition. Now this partition Q0 and Q4 cannot be further disintegrated. Okay, so there's no point in checking them. Now we have to check Q1, Q2 and Q3. So Q1 goes to the same partition on input 0 and final partition on input 1. Q2, same partition on input 0, final partition on input 1. Q3, same partition on input 0, final partition on input 1. Okay, so all these three states behave more or less similarly. So we do not have any reason to break them up or and separate them into separate blocks. Okay, so the next iteration you find remains the same. Okay, the same partitioning, the partitioning remains the same. So P1 and P2, so one iteration to the next, there has been no change in the subsets which we find. Okay, so we can stop our disintegrating process here. So what this means is that Q0 has to be a separate state in the final DFA. Q4 has to be a separate state, which is also the final state, of course. And these three states, because they are behaving similarly, they can be merged into the same state, into a single state. Okay. So we infer that states Q1, Q2 and Q3 are equivalent and can be merged together. Okay, so Q1, Q2 and Q3, you see they are equivalent and can be merged together. On input 0, they go to the same partition. On input 1, they have a transition to Q4. Okay. And Q0C on input 0, it goes